At first, it seemed like just another storm forming far from land. Meteorologists monitoring weather systems across the ocean noticed a developing area of low pressure accompanied by clusters of thunderstorms. Similar systems appear every year, and many never become significant threats. Some weaken after encountering unfavorable atmospheric conditions. Others bring moderate rainfall and strong winds before gradually dissipating. Nothing about this particular storm initially suggested that it would become the focus of growing concern among weather experts. Yet over the following days, something began to change. Satellite images revealed a system becoming increasingly organized. Thunderstorms started wrapping more tightly around the center. Atmospheric conditions that normally limit storm development remained surprisingly favorable. Slowly but steadily, the storm began intensifying. As warm ocean waters fueled the developing system, meteorologists observed pressure levels falling within the storm's core. In tropical weather systems, lower central pressure often corresponds with stronger winds and greater organization. Weather models that had originally predicted only modest strengthening started showing more concerning possibilities. Forecast tracks extended farther. Intensity projections increased. Emergency management agencies began paying closer attention. While there was still uncertainty regarding the storm's ultimate path and strength, experts agreed on one important fact. The system was growing more dangerous. One of the primary factors driving the storm's development was unusually warm ocean water. Tropical storms and hurricanes derive their energy from heat stored within the upper layers of the ocean. When sea surface temperatures remain elevated across large regions, storms can access enormous amounts of energy. Warm water evaporates into the atmosphere, where it later condenses into clouds and thunderstorms. This process releases heat, further strengthening the storm. In this case, ocean temperatures along the projected path remained favorable for continued development. Rather than encountering cooler waters that might weaken the system, the storm appeared positioned to remain over a powerful energy source. At the same time, atmospheric conditions were aligning in ways that favored intensification. One of the most important factors influencing storm strength is vertical wind shear. Wind shear refers to changes in wind speed and direction at different altitudes. Strong wind shear can disrupt developing storms by displacing thunderstorms away from the circulation center. Weak wind shear, however, allows storms to organize more efficiently. Meteorologists monitoring upper-level winds noticed that shear values across the region remained relatively low. This meant the storm could maintain its structure while continuing to strengthen. Satellite imagery became increasingly dramatic with each passing day. Meteorologists observed dense clusters of thunderstorms forming near the center of circulation. Cloud tops reached extremely high altitudes, indicating powerful upward motion within the storm. Infrared satellite sensors revealed very cold cloud top temperatures, a sign of intense thunderstorm activity. Visible satellite images showed curved bands of clouds wrapping around the center in a pattern associated with strengthening tropical cyclones. To experienced forecasters, these developments suggested that the storm was entering a more dangerous phase. Forecast models began showing the possibility of rapid intensification. This phenomenon occurs when a storm gains strength at an unusually fast rate over a relatively short period. Rapid intensification has become one of the most challenging aspects of tropical cyclone forecasting because it can dramatically alter the threat level in a matter of hours. Communities expecting a moderate storm may suddenly find themselves facing a major hurricane. Advances in meteorology have improved forecasting capabilities, but rapid intensification remains difficult to predict with complete accuracy. As a result, emergency planners often approach such situations with heightened caution. The growing storm also raised concerns regarding rainfall potential. While powerful winds often receive the most attention, flooding frequently causes some of the most severe impacts associated with tropical systems. Large storms can transport tremendous quantities of moisture from the ocean into surrounding regions. As that moisture condenses into rain, some locations may receive extraordinary precipitation totals. Rivers can rise rapidly. Urban drainage systems may become overwhelmed. Flash flooding can develop with little warning. Meteorologists examining moisture data associated with the storm noted that atmospheric conditions supported the possibility of very heavy rainfall wherever the system eventually moved. Storm surge represented another major concern. When powerful storms approach coastlines, strong winds push seawater toward land. This rise in water level can inundate coastal communities, damage infrastructure, and create life-threatening conditions. Storm surge often extends far beyond the immediate coastline, especially in areas with shallow coastal waters. Emergency managers closely monitored surge projections because even a slight increase in storm intensity could significantly increase flood risk for vulnerable locations. History has repeatedly demonstrated that storm surge can be among the most destructive hazards associated with tropical cyclones. As media coverage expanded, public interest in the storm increased dramatically. Weather enthusiasts tracked satellite updates around the clock. Residents in potentially affected regions began monitoring forecasts more closely. Emergency preparedness officials reviewed response plans and communication strategies. Although the exact path remained uncertain, the overall trend was becoming increasingly clear. Nearly every new forecast cycle indicated a stronger and more organized system than previous projections had suggested. One reason storms can become so dangerous is the complexity of atmospheric interactions influencing their behavior. Tropical cyclones do not exist in isolation. Their movement and intensity depend on surrounding weather patterns, ocean conditions, humidity levels, atmospheric stability, and numerous other factors. Small changes in any of these variables can alter future outcomes. This complexity explains why forecasts often evolve over time. Meteorologists continuously analyze new observations, update computer models, and refine predictions as additional data becomes available. Aircraft reconnaissance missions provided valuable information about the storm's internal structure. Specially equipped aircraft flew directly into the system to collect measurements unavailable from satellites alone. These missions recorded wind speeds, pressure readings, temperature profiles, and moisture levels. Instruments released from the aircraft transmitted detailed atmospheric data as they descended through the storm. The information helped forecasters better understand current conditions and improve forecast accuracy. Several reconnaissance reports indicated that the storm's core was becoming increasingly organized, reinforcing concerns about continued strengthening. As the storm evolved, experts emphasized the importance of preparedness rather than focusing solely on exact forecast details. While many people naturally concentrate on projected tracks, hazardous conditions can extend far from the center of a storm. Strong winds, heavy rainfall, tornadoes, rough surf, and coastal flooding may affect regions well outside the forecast landfall zone. Emergency officials encouraged residents in potentially affected areas to review emergency plans, gather supplies, and remain informed through reliable weather sources. Preparation becomes especially important when dealing with storms capable of rapid changes in strength. As media coverage expanded, public interest in the storm increased dramatically. Weather enthusiasts tracked satellite updates around the clock. Residents in potentially affected regions began monitoring forecasts more closely. Emergency preparedness officials reviewed response plans and communication strategies. Although the exact path remained uncertain, the overall trend was becoming increasingly clear. Nearly every new forecast cycle indicated a stronger and more organized system than previous projections had suggested. One reason storms can become so dangerous is the complexity of atmospheric interactions influencing their behavior. Tropical cyclones do not exist in isolation. Their movement and intensity depend on surrounding weather patterns, ocean conditions, humidity levels, atmospheric stability, and numerous other factors. Small changes in any of these variables can alter future outcomes. This complexity explains why forecasts often evolve over time. Meteorologists continuously analyze new observations, update computer models, and refine predictions as additional data becomes available. Aircraft reconnaissance missions provided valuable information about the storm's internal structure. Specially equipped aircraft flew directly into the system to collect measurements unavailable from satellites alone. These missions recorded wind speeds, pressure readings, temperature profiles, and moisture levels. Instruments released from the aircraft transmitted detailed atmospheric data as they descended through the storm. The information helped forecasters better understand current conditions and improve forecast accuracy. Several reconnaissance reports indicated that the storm's core was becoming increasingly organized, reinforcing concerns about continued strengthening. As the storm evolved, experts emphasized the importance of preparedness rather than focusing solely on exact forecast details. While many people naturally concentrate on projected tracks, hazardous conditions can extend far from the center of a storm. Strong winds, heavy rainfall, tornadoes, rough surf, and coastal flooding may affect regions well outside the forecast landfall zone. Emergency officials encouraged residents in potentially affected areas to review emergency plans, gather supplies, and remain informed through reliable weather sources. Preparation becomes especially important when dealing with storms capable of rapid changes in strength. The ocean beneath the storm continued providing abundant energy. Measurements indicated not only warm surface temperatures, but also significant heat content extending deeper below the surface. This detail is important because powerful storms can churn cooler water upward as they move. When warm water extends deeper into the ocean, this cooling effect becomes less significant, allowing storms to maintain or even increase their intensity. Oceanographers and meteorologists studying these conditions recognized that the environment remained highly supportive of further strengthening. Computer forecast models showed increasing agreement regarding the storm's future development. Although differences remained concerning exact intensity and track details, the broader message was consistent. Environmental conditions favored continued organization. Atmospheric obstacles remained limited. Ocean temperatures remained supportive. The storm had already exceeded some earlier expectations, and there was growing concern that additional strengthening could occur before land interaction or less favorable conditions eventually intervened. Public attention often focuses on dramatic satellite images showing the eye of a hurricane or the swirling cloud structure of a major storm. However, meteorologists understand that some of the most important warning signs appear long before such features become visible. Falling pressure, improving organization, persistent thunderstorm development, favorable environmental conditions, and strengthening circulation all contribute to the overall assessment. In this case, nearly every indicator pointed in the same direction. The storm was becoming stronger, more organized, and potentially more dangerous with each passing day. By the end of the monitoring period, what had once appeared to be an ordinary tropical disturbance had transformed into a significant weather threat commanding international attention. Forecast centers issued increasingly urgent updates. Emergency agencies prepared for multiple scenarios. Coastal communities watched the latest advisories closely. While uncertainty remained regarding the precise outcome, one reality had become impossible to ignore. The storm was continuing to grow, atmospheric conditions remained favorable, and the risks associated with the system were increasing. Meteorologists had witnessed countless storms over the years, but they understood that some systems possessed the potential to evolve rapidly from routine weather events into major disasters. As new data arrived and forecasts were updated, concern continued growing. The storm was no longer simply developing. It was entering a dangerous stage, and all signs suggested that its most powerful phase might still lie ahead. As the storm continued its journey across open waters, meteorologists became increasingly concerned about the speed at which conditions were changing. Every new set of observations revealed a system that appeared stronger, larger, and more organized than it had been just hours earlier. Satellite imagery showed powerful thunderstorms continuously erupting around the center of circulation. Thick cloud bands wrapped tightly around the storm, creating a structure often associated with significant tropical cyclones. Weather experts monitoring these developments understood that such changes were not merely cosmetic. They indicated that the storm was becoming more efficient at drawing energy from the ocean and converting that energy into stronger winds and more intense weather. One of the most alarming developments involved the formation of a clearly defined inner core. In powerful tropical systems, the inner core acts as the engine that drives the storm. As thunderstorms consolidate around this central region, pressure often falls further, allowing winds to accelerate. Aircraft reconnaissance teams flying through the system reported increasingly organized wind fields and stronger gusts. Instruments recorded changes that suggested the storm was approaching another phase of intensification. While forecasts had already anticipated strengthening, some observations hinted that the process might be occurring faster than expected. Meteorologists paid close attention to pressure readings because they often provide valuable clues about future behavior. As central pressure decreases, the difference between the storm's center and surrounding atmosphere becomes greater. This pressure difference helps generate stronger winds. During several observation periods, forecasters noted significant drops in pressure within relatively short time frames. Such trends often serve as warning signs that a storm is intensifying rapidly. Although pressure alone does not determine the overall danger posed by a system, it remains one of the most important indicators used by weather experts around the world. Meanwhile, ocean conditions remained exceptionally favorable. The storm continued moving over waters capable of supporting powerful tropical development. Not only were sea surface temperatures unusually warm, but heat extended well below the surface. This deeper reservoir of energy reduced the likelihood that the storm would weaken itself by stirring cooler water upward. In many historical cases, storms have lost strength after mixing cooler water into the upper ocean. Here, however, the available heat remained abundant. Every hour spent over these waters provided additional fuel for the storm's circulation. Forecast discussions increasingly referenced the possibility of major impacts if the storm maintained its current trajectory. While exact landfall locations remained uncertain, emergency management agencies understood that preparations often require significant time. Communities located near coastlines reviewed evacuation plans, emergency shelters, communication procedures, and resource distribution strategies. Officials emphasized that waiting until the final forecast is issued can leave insufficient time for action. Storms capable of rapid intensification can dramatically alter local risk levels within a very short period. Heavy rainfall remained among the most serious concerns. Large tropical systems often transport vast amounts of moisture through the atmosphere. As this moisture converges and rises, it can produce prolonged periods of intense rainfall. Some forecast models suggested that certain regions could experience rainfall totals, measured not in centimeters, but in extraordinary amounts capable of overwhelming drainage systems and causing widespread flooding. Rivers and streams already elevated from previous rainfall events could become particularly vulnerable. Flooding often extends far inland, affecting locations many kilometers from the coastline and creating hazards long after winds begin to weaken. Storm surge projections also became more troubling as intensity forecasts increased. Storm surge develops when powerful winds push ocean water toward shore, causing water levels to rise above normal tides. In vulnerable coastal areas, this process can inundate roads, homes, businesses, and critical infrastructure. The danger is often underestimated because surge does not arrive as a dramatic wave, but rather as a rapidly rising body of water that advances inland. Historical disasters have repeatedly demonstrated that storm surge can be one of the deadliest aspects of tropical cyclones. Emergency planners closely monitored updated projections, as each increase in storm intensity translated into greater coastal flooding potential. Another challenge involved the sheer size of the weather system. Large storms can affect enormous geographic areas simultaneously. Even locations far from the center may experience strong winds, heavy rain, dangerous surf, and isolated tornadoes. Forecasters stress that focusing exclusively on the projected center track can create a false sense of security. Weather hazards often extend hundreds of kilometers from the storm's core. As a result, communities outside the immediate forecast path were also urged to remain alert and prepared for changing conditions. The atmosphere surrounding the storm continued supporting development. Humidity levels remained high, reducing the amount of dry air capable of disrupting thunderstorm formation. Upper-level winds provided efficient outflow channels that allowed rising air within the storm to escape and be replaced by new inflows from below. This process helped sustain vigorous thunderstorm activity around the center. Meteorologists often compare such systems to heat engines, and in this case, nearly every environmental component appeared favorable for continued operation. Computer forecast models underwent frequent updates as new observational data became available. While individual models still differed regarding specific details, overall confidence increased that the storm would remain a major threat. Ensemble forecasts, which combined numerous model simulations, showed a growing concentration of solutions supporting a stronger storm scenario. Such agreement among models often increases forecaster confidence, although experts remained careful to emphasize the inherent uncertainties associated with tropical cyclone prediction. As media coverage intensified, public interest surged. Television broadcasts, online weather platforms, and social media channels provided continuous updates. Satellite loops showing the storm's evolution attracted millions of viewers. Meteorologists participated in interviews explaining forecast uncertainties, potential impacts, and preparedness recommendations. The visual appearance of the storm became increasingly striking, with satellite imagery revealing a nearly symmetrical structures often associated with powerful systems. To weather experts, however, the significance extended beyond aesthetics. A more symmetrical storm frequently indicates greater organizational efficiency and the potential for further strengthening. Emergency supply stores in some regions began experiencing increased demand. Residents purchased bottled water, batteries, flashlights, non-perishable food, fuel, and emergency equipment. Hardware stores reported interest in storm shutters, generators, and protective materials. Local authorities reminded the public that preparedness should occur before severe conditions arrive. Once tropical storm force winds begin affecting an area, many emergency activities become significantly more difficult and dangerous. The aviation community also monitored developments closely. Major storms can disrupt air travel across large regions, affecting routes far from the storm itself. Airlines reviewed contingency plans while meteorological agencies provided specialized forecasts to support operational decisions. Maritime interests faced similar challenges. Shipping companies adjusted routes to avoid hazardous conditions, while ports evaluated procedures for securing facilities and protecting vessels. Meteorologists noted that even if the storm eventually weakened before reaching land, dangerous impacts could still occur. Tropical systems often maintain large moisture fields and extensive wind circulation, despite fluctuations in peak intensity. Heavy rainfall, flooding, rough surf, and coastal erosion can remain significant threats regardless of whether a storm reaches its maximum projected strength. This reality underscored the importance of preparedness across a broad area rather than focusing solely on the strongest portion of the system. As nighttime satellite imagery arrived, forecasters observed continued thunderstorm development near the center. Lightning activity increased in certain regions of the storm, while infrared imagery revealed exceptionally cold cloud tops indicative of powerful upward motion. These observations suggested that the atmosphere remained highly unstable and supportive of further strengthening. Each new data cycle reinforced the conclusion that the storm had not yet reached its peak intensity. By this stage, the transformation from a routine tropical disturbance into a major weather threat was undeniable. What began as a relatively unremarkable area of low pressure had evolved into a system commanding the attention of meteorological agencies, emergency planners, government officials, transportation networks, and millions of residents. Forecast discussions became more urgent. Preparedness messaging intensified. Communities evaluated risks and reviewed emergency plans. While uncertainties remained regarding exact impacts, the overall trend was unmistakable. The storm continued growing more dangerous. Ocean conditions remained favorable. Atmospheric support persisted. Forecast models indicated further development. Rainfall threats increased, storm surge projections expanded, wind forecasts strengthened. Every available indicator suggested that the system still possessed significant potential for additional intensification. Meteorologists knew that tropical cyclones can change rapidly, but they also understood when environmental conditions align in ways that demand heightened concern. In this case, the evidence was mounting from every direction. The storm was stronger than before, the hazards were increasing, and the period of greatest danger might not have arrived yet. As forecasters continued monitoring the evolving system, one message remained consistent across every update. The storm was still strengthening, and communities in its potential path needed to prepare for the possibility of severe and far-reaching impacts.